I introduce you to the audience, okay? Professor Guilherme Camus é professor hoje do Instituto de Minas de Saint-Étienne, na França. Ele é diretor do grupo de Física e Mecânica dos Materiais. Obteve seu mestrado em Engenharia Mecânica em 2002 e o seu PhD em Ciências Mecânicas na área de Tribologia e Mecânica dos Materiais em 2005 pela École Centrale de Lyon, na França. Tem experiência de pós-doc na McGill University com o professor Kromek e tem uma vasta experiência internacional. Estará apresentando hoje o seu trabalho para nós. Professor, you are with the time now for your presentation. Okay, I will translate your presentation.
Okay, so thank you, Samuel, for the invitation and for the presentation. So it's my pleasure to present the work in my group. So the presentation of today deals with the thermonuclear fusion applications and materials for thermonuclear fusion. So this is a joint work with some of my colleagues in France. So CEA here, that is the Center for Atomic Energy in France, and the Institut Fresnel, that is a team in the south of France that deals with high temperature engineering. Okay, so let's start. Sorry. Okay, so a few words about thermonuclear fusion. So I think that some of you know about these topics for years. So the concept beneath the nuclear fusion is that when you have two atoms that are close enough, they can fuse to produce a new atom, and finally it generates a huge amount of heat. So usually what we consider is the fusion between deuterium and tritium to form helium and a neutron here. And you can see here the energy of the reaction. So clearly, if we are able one day to deal with thermonuclear fusion, that should significantly reduce the world's carbon footprint. But this is not for now. This is maybe for the next century. So now, in terms of engineering, how to deal with thermonuclear fusion, so we have to use what we call a tokamak. So the nuclear reaction has to happen into a plasma that is about a few millions of degrees hot, so the plasma here. So you can understand that the plasma cannot be in contact with any solid materials, so it has to be confined, and this is magnetically confined in a vacuum chamber. You can see here what looks like a tokamak, so the ITER tokamak in France. So that is, I would say that is under building now. So this is 30 meters here in dimension, 30 meters in this dimension, and the plasma will be here. Okay. This is the divertor. This is the material that has to face the plasma here. Okay. So it's quite huge. So you can understand that finally one of the main issue in thermonuclear fusion first is to achieve fusion, okay, but it's also to find the materials that can resist to this kind of nuclear reaction. So we have to design some units that we call plasma facing units. So in the divertor, that is able to resist high heat flux, that can resist neutron and ion irradiation, and that should resist to erosion, just to make sure that there is no impurities in the plasma. So the materials for that has been chosen. This is the tungsten that has a very high melting point, and clearly the materials here, okay, is made of tungsten. So so I would say what is a plasma facing units? This is an assembly of tungsten monoblocks. Okay, that are cooled with a liquid that flows into a copper tube here. So each block that you can see here is quite huge in dimension. So I'm sorry, there is a mistake somewhere, but clearly each PFU is constituted of 140 tungsten blocks, and there is 2,000 PFUs in ITER, basically, so in one reactor. So that means 80 tons of tungsten just to resist the plasma. So it's huge. Now, if we look to what happened to the tungsten during the loading, so the tungsten here will be loaded up to 2,000 degrees sometimes, okay, and a few millimeters beneath the surface, this will be 1,000 degrees. So the duration of the heat flux is about 10 seconds. So what happens is that this is a cyclic thermal load between 100 degree and 2000 degree, basically. Okay, so this is a cyclic load. So when there is a cyclic solicitation, clearly there is some damage that can happen in the material, and there is some thermal damage. So clearly, designing plasma facing units deals with fatigue damage. So let's now focus to what happened on a single monoblock. So you can see here a finite element model, so classical model, heat flux. Clearly, you can see the temperature gradient in the material. So between 1,800 and here you have 1,000 degrees Celsius. And so if you look to the microstructure of the material after a given number of cycles, so maybe after 10 cycles, you will see that the materials here is a bit different from the material in the depths. So to understand that, you have to consider that when the material is red, it means that this is the raw material. It has been, I would say, warm rolled, in this case for tungsten. So there's a lot of deformation. That's why it's a red. Okay, and here you have just some single color, and so that means that the grains are perfectly recrystallized. So there is a recrystallization that happens in the near surface after a given number of cycles. And so if you look to what happened to the monoblocks in terms of damage, you can see a crack that will propagate from the surface to the copper tube here. So this is something that matters, because if there is a crack and that the plasma enter into the crack and goes to the copper tube, there will be melting of the copper. So there will be some issue with that. So we have to prevent this crack. And what we know is that this crack is finally driven by the recrystallization. So why recrystallization drives the crack? So we will see that from thermal fatigue curve. So just to understand this kind of curve, here you have on this axis the plastic strain that happens during a cycle, and here the number of cycles to failure. So if we consider the black curve here, so this is the fatigue curve for the material at room temperature. If you have a plastic strain about 10-1, the number of cycles to failure will be 11, something like that. If it is 10-2, so 10 times lower, this will be 10-4 cycles to failure. Okay. Now, if we consider the material, so here we have the fatigue curve at high temperature, so 800 degrees C, and you have the fatigue curve for the raw material. So before recrystallization, the red part, you can see here the stress strain curve here, and here the one for the recrystallized material. So what we call the softened tungsten. It has been recrystallized, so it's softer. What you can see is finally there's a shift from this curve to this curve. So recrystallized material finally is I would say that it's better to use non-recrystallized material from this curve. So recrystallization will play on this, but recrystallization will also play on the plastic strain level because the yield stress is lower. So at each cycle, you will have more, much more plastic strain for a given for a cycle. Okay, so recrystallization clearly is not very good for fatigue. And the second aspect is that if there is some plastic strain that happen at a low temperature, finally you have to consider this curve to design the fatigue damage. Okay. And this curve is related to the ductile to brittle transition temperature. So recrystallization will play on the DPTT, okay, but it will also play on the plastic flow that happen on each thermal cycle, during each thermal cycle. So if we want to optimize a PFU lifetime, this is clearly of primary importance to model and predict the recrystallization kinetics of tungsten materials, and that's the aim of this talk. So just a few words about recrystallization. So recrystallization is a metallurgical mechanism that is related to restoration mechanism. Restoration means that with temperature, with heat treatment, there will be a decrease of the mechanical properties, a softening of the material. So there is two classical restoration mechanisms at play. The first is static recovery. So the concept is to decrease the density of dislocation and reorganize with temperature the dislocation into subgrains. And the material here is clearly softer than this one. This is a quite slow mechanism to decrease the mechanical properties. And the second one is recrystallization. So this is totally different because in this case, in the microstructure, there will be a new grain that nucleate, usually at the grain boundary. And this new grain here will grow at the expense of the former microstructure. And this is driven by the stored energy in the materials, that means the dislocation density. So these are two different mechanisms that can happen at high temperature. And they can compete. So you can see here what happened at a temperature of 1,200 degrees Celsius. First, you have a decrease of the hardness of the material with time, that it deals with recovery. And after a given time, there will be a decrease due to recrystallization. Usually, the decrease of the mechanical properties due to recrystallization is significantly higher than the decrease due to recovery only. What we know is that recovery and recrystallization can coexist in the material at a given temperature. Here you have the same result, but at a higher temperature, so 50 degrees higher. And so the main difference is finally the time scale. Here, to start the recrystallization, here you need 30 hours, and here it's about 300 hours. Just remember that in the case of some thermonuclear fusion applications, sometimes the temperature can be really larger than that, higher than that, about sometime 2000 degrees Celsius. You can see here the effect of temperature and strain on recrystallization. So if you increase the temperature, it's what I told before, I said before. So you increase the recrystallization rates. And if you increase the strain in the material, the stored energy in the material, so it depends on the thermomechanical process you use to finally get the tungsten material. So you increase also the recrystallization rates. So the higher the temperature or the strain, the higher the recrystallization rate. And here you have an example of what happened on a microstructure with a gradient inside. So this is a microstructure that has been obtained with severe plastic deformation, but with some shear. So the plastic deformation was very high here and was a bit lower here. You can see that there is a gradient of microstructure. Here you have a huge grain size with some disorientation inside. And so if you apply here, it is on copper and not tungsten, because we cannot do that on tungsten. If you apply a heat treatment 300 degrees Celsius during 30 minutes, here is the results you obtain in terms of microstructure. You can here see that the resulting microstructure depends on the depths. Okay, so here you have some small grains that correspond to this microstructure. Here the grains are larger, and here we have no recrystallization. This is only recovery. Okay, so recrystallization happens here and recovery is here. So that is to say that finally, static recrystallization and recovery kinetics depend upon the initial microstructure and the stored energy. Okay, so if we want to deal with the recrystallization kinetics, we want to optimize PFU, we have to optimize the initial microstructure of the material. So now, how to predict lifetime of PFU? We have to predict the restoration kinetics of tungsten materials under thermonuclear fusion conditions. So we have to measure the restoration kinetics at high temperature. That's not so easy to do. We have to determine methods for characterizing the microstructural states related to recrystallization. And finally, we have to develop some model for that purpose. So let's start with the investigation of the recrystallization of tungsten at high temperature. So with our colleague of Institut Fresnel and CEA in France, a specific platform has been built to perform heat treatment at very high temperature. It is based on a laser-based facility. You can see here the laser, okay, that go through a vacuum chamber and that heats a sample. Sorry. So this sample is irradiated on both sides, and the temperature rise up to a very high temperature here, 2000 degrees, clearly. Here you can see what happened on the sample. So this is a real-time experiment. So the temperature reached 2000 degrees in less than 2 seconds. Okay, so we have a heating rate that can go up to 1000 degrees per second, and then we can stabilize the temperature. We can regulate the temperature. Here you can see a test to show you that the regulation of the temperature is quite good. So here is the heating stage, and then you have the temperature regulation that can last 3 hours. So we can perform heat treatment between a few seconds to a few hours, between 900 K to 3800 K. So why using this kind of setup and not a classical oven that can reach very high temperature? It's because the heating stage has a significant effect on recrystallization of tungsten at very high temperature. You can see here the results of a heat treatment. So at a temperature about 1350 degrees Celsius during 1 hour. Okay. Here, the microstructure at the end with the laser-based facility. So a fast heating rate. And here with the classical oven, so this is 5 degrees per minute. And you can see here in blue, it's the recrystallized grain. And here you can see that there is no recrystallized grains. So clearly, you won't get the same kinetics of recrystallization because recrystallization starts during the heating stage in this case. So we have to use this kind of setup to go at very high temperature. Okay, so let's now present some results. With this setup. So here you can see a recrystallization kinetics at high temperature, so 1500 degrees Celsius. It's so on a tungsten that can be used for ITER classically. So you can see here the evolution of the recrystallized fraction. So that means the ratio between the white area here and the hull area on the microstructure. And you can see here that the recrystallized fraction increases with time till it reaches 100% of recrystallized fraction. So we have a small discrepancy between recrystallized fraction measured from microstructural measurement here or with hardness measurement. But it comes from the fact that with hardness measurement, you have to consider also the competition with recovery that we don't see with microstructural measurement. Now, how to use this kind of results to design new kind of PFU? So we compared here two materials, two tungsten with two different suppliers, from two different suppliers. One with a recrystallized fraction of 13% here. The second one with a recrystallized fraction of 8%. The difference is not significant up to us, but the main difference is in the microstructure. You can see here that finally the stored energy, the red in the microstructure is clearly lower in this image than in this image. Okay, so there's a difference. So how to analyze that? So here you can see the results of the heat treatment, so at different temperature. So here this is the annealing time to reach 50% of recrystallized fraction. And here it is the annealing temperature. If you consider the temperature of 1,500 degrees Celsius, so clearly to reach 50% of fraction recrystallized with the batch A, you need 500 seconds. With the batch B, it's about 1,000 seconds. So regarding PFU lifetime, it's better to use batch B materials. The question is why grade B recrystallization kinetics is slower than the grade A1. So we can answer to that question by using some measurement at the microstructure scale. So basically it's based on hardness measurement, but not macroscopic hardness, but what we call nano indentation, so nano hardness. So we can perform hardness measurement at the scale of grain. And so we can make a lot of indents on a given microstructure and then plot the hardness distribution. You can see here the results for the recrystallized sample. So that means that the sample is fully recrystallized. You have this distribution of hardness that corresponds finally to the different orientation in the material. And here you can see the results for the two grades, the two batches, batch A in blue and batch B in red. And what you can see, it's clear there is a difference in the hardness distribution between grade B and grade A. Clearly, hardness of grade E is higher in terms of nano hardness. That means that there is much more stored energy in grade A. And finally, it correlates with what we measure here on this curve. So the difference between the two batches is related to the stored energy in the material. So from this kind of experiment, what we can do is to measure what happened after some heat treatment. And you can see the hardness distribution that will shift from the right to the left here. So this is a consequence of recovery of materials and not a recrystallization. So it happens with time or with temperature. And so clearly from that kind of measurement, we are able to measure the recovery kinetics. Recovery, what does it mean? It means this is the decrease of dislocation density in the material. And from hardness, we can relate hardness to the stress, and we can relate the stress to the dislocation density. So we are able, with this kind of measurement, to estimate the dislocation density and to analyze the decrease of the dislocation density with time. Okay, and from that, we are able to measure the parameters that are related to recovery for the different temperature that we tested. So we use this kind of data to evidence recovery. Now the last part is how to model that, because we need to model recrystallization and recovery to know finally the lifetime of PFU. There is many kind of model. So there is some macroscopic model based on Avramic kinetics. This is what we use in terms of an industrial application usually. So that means that we make a lot of experiments and we try to fit this experiment with some Avramic kinetics. On the other side, this is the academic view. And so we try to model each grain separately and we let the recrystallization happens. So here the computation time is very costly. Here it's very rapid, but you need a lot of experiments. In between, there is some mean field modeling that we use. Finally, that consider each grain separately, but you don't need to model all the grains because a grain is related to what happened to the average microstructure. Okay, so we use some physical parameters here, but the computation time is quite low. So here are basically the equation that we have to use to model recrystallization and recovery. So the first equation is the decrease of the dislocation density with time. Okay, so here it's the dislocation density, and this is the recovery parameters. And the second equation is the movement of the grain boundary. So the increase of the grain size that depends on the stored energy that is here, and that depends also on the grain radius. And here you can see these parameters, that is the grain boundary mobility. Then we can work on the full microstructure. And so with this algorithm, I won't detail it, we can model the kinetics. So to use this model, we need to identify this parameter and this parameter. This one is known. This one, we can get it from nano-orientation experiments or RNEST data. You can see that for grade A and grade B, finally, this is the same recovery parameters. We have the same results. And we can deal with the grain boundary mobility in the same manner. This is almost the same result for grade A and grade B. So that means that the main difference between the two tungsten is the initial microstructure and not really the intrinsic physical parameters. So from that, we can try to model the recrystallization kinetics, and you can see that it works quite well. We can fit quite well the data from this kind of mean field model. And finally, just by changing the initial microstructure, you will get another kinetics for the recrystallized fraction. So we use this kind of model to take into account the initial microstructure and finally to find the good initial microstructure. So I am at the end of the presentation. So what we're doing now is to try to develop new method of characterization to work on the initial state, because we know that we have to define the best initial state of the tungsten to optimize the lifetime of PFU. We design new high temperature experiments, and also we try to account model, I would say, irradiation effects during fusion. So thank you for your attention. Do you hear me?
Pode me ouvir?
Yes. Okay. Thank you.
Thank you for your brilliant presentation. So if somebody has a question, okay, it's open for the question now. Somebody has a question? No question? I have a question, Professor. During your presentation, what is like an amazing result that it surprised me a lot was about that the softening that happened in the material. We see that the density of dislocation decreased, but This normally lead to a high hardness. And the tungsten, we saw that the recrystallized grain led to higher hardness. How could you explain this? Like that's the opposite of what normally happens to metal alloys.
So I wouldn't say that the hardness is lower for non-recrystallized materials. So if you look to this result, so I go back to this one. Here it's the hardness of the recrystallized sample, and here it's the hardness of the initial material. So yes, you have a decrease of the hardness with recrystallization, a lowering of the dislocation density. So, in fact, what is very surprising with tungsten is that usually for most of metals, when there is some recrystallization, that means that the material is softer, but it means also that the material can resist to ductile damage. And this is not the case of tungsten. So in the case of tungsten, so if I try to go back to this slide, that's something that can be interesting for you. Okay.
Mostra o slide dele. Mostra o slide, por favor.
Yeah, this is this slide. Okay. What you can see is that if you have a recrystallized tungsten, this is the blue curve. Finally, the fatigue curve is worse than the unrecrystallized fatigue curve. So this is the only material for which we get this kind of results. So that was a bit surprising first. But for most materials, this is the opposite. But in terms of hardness, this is like any materials. The hardness decreases with the dislocation density.
Thank you. Thank you very much for your answer. I have one more question from the audience.
Hi, Professor Carmouche. Thank you for your presentation. I have a quick question about the heating method that you choose. Why you choose such a complex heating system with lasers as opposed to another heating system that would be, let's say, a furnace or electric resistance that will be enough to reach the very high heating rates that you need?
Okay. So with the furnace oven, most of time the heating rate is quite low. So you can use some specific furnace that can go to higher heating rate. So based on induction, basically, we can use resistive heating, but in the case of tungsten, for us, that was easier to use laser heating, a laser heating setup, and some pyrometer and thermal camera to regulate the heating. So that's why we choose that. And in a way, up to us, it was simpler that using another kind of heating device. We tried induction, it was not so easy. So that's why we moved for that. And now it works quite well, so it's not so complex.
Okay, thank you. Thank you for your answer. And I speak português a little bit just a moment. Como foi falado ontem na palestra, né, cooperação internacional entre a indústria e a academia, e são exemplos de trabalhos que são feitos que a indústria pode ganhar, tá? Com experimentos, simulações feitas em laboratórios. A indústria não tem tempo de fazer um trabalho desse ali dentro do reator ali nuclear ali a plasma, ou seja, trazer uma situação de simulação, fazer um offline, um experimento no laboratório, ou seja, isso é um ganho muito que a academia traz de benefício para a indústria. Então, é o nosso propósito, é o propósito desse congresso, é trazer trabalhos e mostrar que é possível. Professor Carmouche, thank you very much for one more time for your presentation, and we are very delighted for your participation in the conference. Okay, thank you.
And thank you for the invitation.
Okay. Ok, pessoal?